Let's see, what we've talked about the last few days is the four, like these vocabulary words. There's really four of them: zero, factor, solution, x-intercept. So we'll start with this zero, which is saying like k is a zero. K is just a placeholder, but it's a zero of the polynomial function and we typically see it written as like x equals k. That's what a zero looks like. And then a factor would be like x, we'll do this different color. X minus k is a factor. So just a reminder of what the vocabulary means and how we want to answer a question with different vocabulary words. So like on your assignment yesterday, or that's due tonight, you were asked, can you write these things in factored form? And can you write the zeros? So you have to do two separate things with them. Okay, so x minus k is a factor of the polynomial f of x. And then we talked about solutions as well. We don't use that one as much, but we might see it, where we say k is a solution of the polynomial equation. And in that situation, we'll see f of k equals 0. And then the final one is the x-intercept. If k is a real number, because it's possible to have imaginary numbers. We don't talk about the imaginary numbers in this course, but it is possible that you could have an imaginary 0 or an imaginary root. So k is an x-intercept of the graph of the polynomial function. And that's where we would say the equation like k comma 0, or the phrase k comma 0. Okay. So we talked about end behavior and how we look at end behavior as a, like, just identifying the degree of the polynomial, identifying the sign as positive or negative. And what we've also kind of talked about briefly is identifying zeros of an equation. And like we've said, potential zeros. But what we can do today is we're going to talk about how to identify the definite number of zeros. And like I said, we've briefly talked about it, but not really. So we're going to look at that today. And this is the fundamental theorem of algebra. It says if f of x is a polynomial degree n, and n is a number that is greater than 0, all right, then the equation f of x equals 0 has at least one solution. Okay. And then the corollary says, this is really important, says if polynomial degree n is greater than 0, then the equation f of x equals 0 has exactly n solutions. Okay, provided each solution repeated twice is counted as 2 solutions. Each solution repeated 3 times is counted as 3, so on and so on. So that's what we're going to kind of look at today, is we're going to look at the number of zeros you might have, and then the number of solutions you might have, as long as they're counted multiple times. So, for example, what I mean by that is like a first degree polynomial is like a straight line, mx plus b, that's a degree 1. how many zeros does it have? Or in other words, how many x-intercepts does it have? It's going to have 1 0. Okay, a second degree polynomial is going to have 2 zeros. A third degree polynomial is going to have 3 zeros. And that's what the corollary to the fundamental theorem of algebra implies. An nth degree polynomial is going to have exactly n zeros. Okay. And so if it's a fourth degree polynomial, it's going to have 4 zeros. A seventh degree polynomial is going to have 7 zeros. One of the key things, though, that's really important is not all zeros are real. I just mentioned that you could have something called imaginary zeros. And you can tell if they're not real zeros by looking at the graph and seeing that they don't have x-intercepts. All right, so maybe a third degree polynomial only has 1 x-intercept. It still has 3 zeros, but it just means 2 of those zeros would be imaginary because we only see 1 x-intercept, so there's only 1 real zero. That's how we can tell the difference between real zeros and imaginary zeros. And in this class, I don't necessarily ask you how to calculate imaginary zeros. I'm just going to ask you to identify if this one has imaginary zeros. All right, that's all I'm asking for. Okay, and even then, I don't think we're going to really deal with it too much in this class. I'm just bringing it up so you're aware of the fact. Okay, so this first example, how many zeros does this function have? F of x equals x cubed plus 5x squared plus 4x plus 20. All we need to do is look at that 3 and say, okay, this one has 3 zeros. Okay, this has 3 zeros. That's it. Example 1b says how many x-intercepts could the graph have? F of x equals x to the 4th minus 8x cubed plus 18x squared minus 27. So it's in descending order correctly. And because it's x to the 4th, this function could have up to 4 x-intercepts. It doesn't mean that it definitely does have 4 x-intercepts. It just means it could have 4 x-intercepts. All right, so it's possible that it has less than 4 x-intercepts. And now we're going to look at some examples of that. Okay, so what we deal with is we could deal with situations where there's multiplicity and repeated roots. All right, so when a factor containing the same root is repeated twice or more, all right, root would also be like a 0. That's almost like the same word. Those words are almost interchangeable. That's called a repeated root. And what that means is, for example, if I gave you, let's start with a single root, which is what we're used to. An equation in factored form, we'll just say x plus 4, x minus 2. And we sketch this. And there's the 2 x-intercepts. That is an example of multiplicity 1. Okay, these are single roots, and we can tell they're single roots just because the line's going to go straight through them at the x-axis. It's basically how the line acts right around the x-axis is what we're looking at. When we look at a double root, you'll see what I mean. Double root could be x minus 1 quantity squared. It could look something like that, where it literally touches the x-axis and then it turns around. That's a double root. So it touches the x-axis, but it doesn't go through. That's what would be considered a double root. which is possible. We can see that. Like here's a factored form equation that shows it. All right. The other way we can tell it's a double root is because it's an x minus 1 quantity squared. It could also be written as f of x equals x minus 1 times x minus 1. But that would still be a double root. Okay. A triple root in factored form, very similar, except this time it's going to say x minus 1 cubed. That would be a triple root. So the root itself is x equals 1, or the 0 itself is x equals 1 in both these situations. But they're going to look a little different on the graph. A triple root on a graph is going to look like this. Like the function is kind of rushing up, and then it slows down as it hits the x-axis, and then it speeds up again, all right, as it goes away. That's a triple root. That's what multiplicity 3 looks like. Okay, so in this case, it kind of flattens as it crosses. It flattens, but then it still crosses the x-axis. And then the last example here, a quadruple root that I'll show you. We'll just say x minus 1 to the 4th. We'll just stay consistent there. And there's a multiplicity 4. And it's going to do the same thing where it's going to flatten and touch the x-axis, but then it's just going to turn around and go back the other way. So it's really hard to visually tell multiplicity difference between a 4 and a 2 on a graph, but so I'm probably not going to ask you like the difference between a 4 and a 2. If you see one, it'll probably just be a multiplicity of 2. But you should just know that that's an even multiplicity where it touches the x-axis and then it goes back in the same direction it was coming from. Okay, so when a factor x minus k is raised to an odd power, it's important to note that the graph will always cross the x-axis. And when a factor x minus k is raised to an even power, the graph touches the x-axis and turns around. That's how we can tell the difference between an odd degree polynomial and an even degree polynomial. Okay. So now our first example here, it just says use x-intercepts to graph each polynomial function. So this is the function that I'm given. F of x equals 1/2 x minus 2 squared. First thing I want to notice is just the x's. There's 1x, there's 2 x's, but then it's squared, so it's technically 3 x's. So if I were asking what's the degree of this polynomial here, turns out this is a 3rd degree polynomial in factored form. Okay, a little harder to tell when it's in factored form than when it's in standard form, but we should still be able to do it. All right, the first thing I want to do is I want to plot the x-intercepts. So this is how we'd graph one of these functions from factored form. And for example, I know x plus 3 is a factor. So one of the x-intercepts is going to be at x equals -3. X minus 2 is a factor. So one of the x-intercepts is going to be at x equals 2. So I'll go ahead and put a scale on my graph. And I'm going to label those points. Positive 2, 0, negative 3, 0. Okay, the next thing I'm going to do is I'm going to determine the end behavior. All right. So for example, as x approaches negative infinity, as x approaches positive infinity. End behavior is determined by the exact same things in factored form as it is in standard form. We need to look at the leading coefficient. In this case, the leading coefficient is 1/2. And we need to look at the degree of the polynomial. The degree is a third degree. So, odd degree, positive leading coefficient. That tells me that this thing from left to right, it starts on a negative side on the left side, so negative infinity as x goes to the left. Positive infinity as x goes to the right. If we don't remember that, that's fine. We just need to go back to our notes from that worksheet where we have it written down. But we should still be able to recognize this is odd degree and, positive leading coefficient because it's positive 1/2. All right, and that's how we can determine end behavior. And then step 3, what I would normally have you guys do is plot the graph. What I'd recommend having you is so that way we just get an idea of what's going on kind of in the middle. So for example, we'd say like, let's go from -3, -2, -1, 0, 1, and 2. So I know that x-intercepts exist at -3, 0, and 2, 0. If I plug in 0 for x, I'm going to get a 4 plus times a 3 is a 12 times 1/2. I'm going to get a 6 for y. If I plug in a -2 for x, I'm going to get an 8 for y. And again, that's just plugging in -2, 1/2 times -2 plus 3 times -2 minus 2 more. So the -2 plus 3 is positive 1. And this becomes -4 squared. I get 1/2 of 16, which is 8. That's where the 8 came from. If I plug in a -1, I get a 9. Plug in a 1, I get a 2. I did this a little earlier, so that's why I have the numbers down already. But right now I'm just trying to show you what this is going to look like so you get an idea. And then we can go ahead and sketch this. Because we know what the end behavior looks like, we know it's going to go from negative to positive. And the other thing we should know is we should know multiplicities. Like right here, this x minus 2, it's going to touch the x-axis and then it's going to turn around and shoot back up. And that matches what the end behavior says it's going to do too. So this is where the multiplicities is super important. Right here, this is multiplicity 2. Because it's in factored form and we know it's going to touch the x-axis and then turn around. This one over here was the x plus 3. That's a multiplicity of 1. And it just goes straight through that point. It doesn't slow down or anything. It just goes straight through. That's how we can tell the difference between multiplicity 2 and multiplicity of 1. And that's what step 4 is going to be, is just draw the graph. Using knowledge of end behavior and multiplicity. And then we've literally just used our table to find values in the middle so we have an idea of what kind of shape it looks like in the middle. Okay. Problem number 2, 2 times x minus 1 quantity squared times x minus 4. This is another example of a degree 3 polynomial. Oops, let's do a different color. It's got a degree there, 2 degrees, 3 degrees. All right. So we should be able to plot the x-intercepts. One of them is x minus 1 equals 0, so add 1 to both sides. X equals 1. The other one's going to be x minus 4 equals 0, add 4 to both sides. X equals 4. 1 and 4. And then we can determine the end behavior again. As x goes to the left, as x goes to the right. Always write it as x goes to the left, x goes to the right. What's f of x doing? And this is another one where it's odd degree, positive leading coefficient. So f of x is going to follow that same trend, the y values. And again, we can just look at our graph if we need to.
Wouldn't it be, as it goes towards infinity, it goes towards positive infinity, and then as it goes towards negative infinity, it also goes towards negative?
So I say that again?
So as x goes to negative infinity, y also goes to negative infinity.
Yes.
And then vice versa for positive. Okay.
Yes, exactly. Yes, thank you. Yeah. Okay, and then if we pick some points here, actually, you know what? I'm going to change my values a little bit. The values I had written down for this one earlier were this. I had 0, 1, 2, 3, 4, and 5. And that's just because I'm trying to work around those x-intercepts. So I know 1 comma 0 and 4 comma 0 is 2 of the points already. And then if I plugged in 0, I'm going to get a negative 8. If I plugged in 2, I'm going to get negative 4. 3 is going to give me a negative 8. And then 5 gives me a positive 32. So 5 is going to be way off the paper. Real fast. And then what I can see is that if I have 3, I get a negative 8. 2, I get a negative 4. And then 1 gives me a 0. 0 gives me another negative 8. Looks something like that. And again, I see a multiplicity 2, where the x minus 1 is. It's going to just touch the x-axis and turn around. And I see a multiplicity 1, where the x equals 4 is. So that's how you can tell the difference between a multiplicity 2 and a multiplicity 1, and the reaction you're going to get there. All right, so now what I've got for you guys is a couple practice problems where I just want you, basically, most important thing is to identify the multiplicity of these, and then see if you can sketch that on the graph, represent that multiplicity, and identify the end behavior as well. Plotting the middle points is useful for the general shape of the graph. You can look that up on Desmos if you want. But before you do that, try and identify the multiplicity and the degree of the polynomial and the end behavior of it. All right, so try these two problems now. Let me know if you have any questions at all. First thing to point out for problem 1 is we see x plus 2, x minus 1, x minus 3. So there's only 3 factors. None of them are squared, so this is a degree 3. And all of them are multiplicity 1. So there's going to be an x-intercept of negative 2, positive 1, and positive 3. All right, that gives you the idea there. So if I were to plot it, I would probably say negative 2, let's see, and then like negative 1, 0, 1, 2, 3, just to try and include as many of those x-intercepts as possible. And then for determining the end behavior, always as x goes to the left, as x goes to the right. And the great question we had just a minute ago was, what if it's a decimal? It doesn't matter if it's a decimal, it just matters if the sign is positive or negative. That's how we would determine end behavior. Because it's a positive leading coefficient, and it's odd degree, that means the end behavior trends in a positive direction from left to right. Okay. Problem number 2 is odd degree. We have an x plus 1 quantity squared, so this one's going to be multiplicity 2. And then an x minus 2. So I'll do x plus 1, x minus 2. There's our zeros. End behavior, degree 3 again. So end behavior is going to be the same thing, whereas x goes to the left, y goes down. As x goes to the right, y goes up. And then when we're plotting these final values here, -2, -1, 0, 1, 2, 3, we know that -1 is a 0, we know that 2 is a 0, and then we can figure out what the rest of the values are as we go. All right, but that's the general idea with these 2 points. I didn't graph them yet, and I will graph them so you guys can take a look at them. Make sure you did it right. But that's the idea here. So remember that this assignment here is optional. It's good practice with the multiplicity, just as long as you get that part down, that's important. And then also remember that worksheet 29 is posted. That is the review. So, and the answer key is also posted for that. So I want you to open that up, check out the review, make sure you're comfortable with all of this material for Thursday's quiz. And then, of course, if you have any questions, let me know. We got a half hour left today, so you can stay on the Zoom call and work with me. And we also have office hours tomorrow from 10 to 11:30. So if you have any questions at all, you can come meet with me during those times. Have a great day. Don't forget to do the grade assignment tomorrow. And we'll see you on Thursday for the quiz. Thanks so much. Bye.
Thank you.
Thank you.
Thank you.
Mr. Street, do you know what's going to be on the graded assignment tomorrow and the quiz Thursday?
I do.
What concepts will be on those?
Oh, what concepts? So the graded assignment tomorrow should be, can you graph something like this? Can you write an equation in factored form? Can you write it in expanded form? And can you show me polynomial addition, subtraction, multiplication, division, those types of things? I think we did addition, subtraction, and multiplication on the last quiz, right? So definitely polynomial division is going to be on, or synthetic division is going to be on the quiz. Can you identify zeros? Can you identify factors? Those types of things, right? That's what the last few homework assignments have all been.
And then is it the same stuff going to be on the quiz on Thursday?
Yeah, that's what you should expect for the quiz. The graded assignment's probably going to be more of a, can you take this problem, write it in factored form, then can you write it in standard form? That would be the type of thing I'd expect for the graded assignment tomorrow. Okay?
Got it.
Yeah.
Thank you.
You're welcome. And if you guys have any questions on that grade assignment, remember my office hours. Check it out in the morning, check out the grade assignment, then come in and ask questions during office hours. That's the best advice I can give you. Don't look at it too late. Okay, let's do 2 and -1.
Hey, Mr. Street.
Yes?
I know it's late by now, but could you go over the last 4 problems on assignment 26?
Yeah, that's not a problem. We can do that. Just give me a second to finish this graph. And then we'll do that. Just going to touch and turn around. Let's go back down to -6 here. Down to -12. Back up to 0 and out of there. There we go. Okay, so that's kind of what these graphs will look like, you guys. Okay, so you said assignment 26 we want to look at.